Greetings, class! Why is the nitrogen in the air we breathe almost entirely unreactive, while the oxygen right next to it keeps us alive? Today, we will study covalent and coordinate bonding fundamentals to solve this mystery. I am absolutely thrilled to guide you through this explainer, where we're going to break down the invisible molecular architectures that literally construct our entire world. As an expert CAIE, AS, and A-level subject specialist, I've designed today's lecture to give you a premium, structured breakdown of exactly how atoms connect, how they interact, and how they dictate the physical properties of the universe. So, let's dive right in, shall we? All right, let's establish our foundational anchor for today's lecture by defining exactly what a single covalent bond is. Fundamentally, it's all about sharing. When we're dealing with non-metal atoms, they really don't want to give up their electrons entirely. It's just not in their nature. Instead, they find a compromise, and they share a pair of electrons. This shared pair becomes the ultimate glue holding the atoms together, creating what we call a bond pair. Understanding this simple, single definition is absolutely the critical first step to unlocking the rest of chemical bonding.
Okay, we're starting our core progression by looking at single bonds. Think of it like this. When two nonmetals combine, they share an electron pair, which is elegantly represented by just a single straight line, like chlorine-chlorine. We see this all the time with simple covalent molecules, whether it's liquid bromine or solid iodine. But if you look really closely at the atomic level, not all electrons actually participate. The outer shell electrons that are left out of the sharing arrangement are called lone pairs. In a single chlorine molecule, for instance, the two atoms share one bonding pair, but each atom retains three lone pairs just kind of sitting on the sidelines. This brilliantly ensures both atoms achieve that highly coveted, completely stable octet configuration of 288.
Here are the core details regarding this topic. Review them intently for their deemed crucial for your finals.
Now, to truly wrap our heads around this, we have to visualize it using dot and cross diagrams. It's a pretty straightforward system. We use a dot for one atom's electrons and a cross for the others. And hey, if you have more than two types of atoms in the mix, you just use additional symbols, like a small circle or a triangle to keep track of who brought what. Drawing these outer electrons in pairs is absolutely vital, because it emphasizes the exact number of bond pairs and lone pairs at just a mere glance. Take methane, for example, featuring a central carbon sharing its four outer electrons, or water, which leaves its oxygen with two distinct lone pairs. It's basically a perfect visual ledger of atomic chemistry. Well, let's see how this builds, because in chemistry, as in life, there are always rule breakers. Not every central atom gets a perfect noble gas configuration of 8. Take boron trifluoride. Boron starts out with an electron arrangement of 2-3, and it shares its three outer electrons with three fluorine atoms that are sitting at 2-7. So boron is basically the broke college student of the periodic table, left electron deficient with only 6 outer electrons. But then, on the exact opposite end of the spectrum, you have sulfur hexafluoride. That central sulfur atom starts at 2-8-6 and shares its 6 outer electrons with 6 fluorines, hoarding a massive 12 electrons around it. This expanded octet is a fantastic reminder that the octet rule is more of a guideline, not an absolute, unbreakable law. So what happens when sharing just one pair isn't enough to reach stability? Well, the atoms simply share more. They can bond together by sharing 2 pairs of electrons, creating what's called a double covalent bond, represented by a double line. Oxygen gas is your classic example here, sharing 2 pairs to complete those outer shells. In carbon dioxide, we see an elegant solution where carbon forms a double bond with each flanking oxygen, satisfying everyone involved. And we see a very similar atomic problem solving in ethene, where 2 carbons share a double bond right in the middle, while still sharing single pairs with 2 hydrogen atoms each. Building on that, some elements push the sharing even further by creating a triple covalent bond. The most vital example of this, and represented by 3 lines, is the nitrogen molecule. Because a nitrogen atom sits at 2,5, it desperately needs to gain 3 electrons to complete its outer shell. To pull this off, 2 nitrogen atoms overlap and share 3 pairs of electrons, forming 3 covalent bonds in a single molecule, and tightly locking the atoms together while retaining just 1 lone pair each. Now keep this incredibly strong triple bond in mind, because it's going to answer that big mystery we introduced at the very start of our lecture.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
All right, let's pivot to a slightly different, honestly, kind of funny bonding scenario: coordinate or dative bonding. I like to call this the ultimate freeloader situation. It forms when one atom provides both of the electrons needed for a shared covalent bond. You essentially need one atom with a ready-to-donate lone pair, and a second electron-deficient atom with an unfilled orbital just waiting to accept it. Take the ammonium ion, for instance. It forms when ammonia combines with a hydrogen ion. The nitrogen generously provides both electrons to the completely empty hydrogen ion, and to distinguish this in our formulas, we represent it with an arrow pointing strictly away from the donating lone pair, right toward the accepting atom.
We actually see this brilliantly illustrated in another fascinating molecule, aluminum chloride. At high temperatures, it just exists as simple AlCl3 molecules, but that central aluminum is totally electron deficient. It still needs 2 electrons to complete its outer shell. It's literally starving for electrons. So what happens at lower temperatures? 2 molecules team up to form a dimer, Al2Cl6. The lone pairs on 2 chlorine atoms step up and form coordinate bonds with the aluminum atoms, acting as bridges between them. So each of those bridging chlorines is forming one standard covalent bond and one coordinate bond. It is just a gorgeous exercise in molecular teamwork.
Now let's transition from how these bonds are actually formed to how they behave physically in the real world. There's a fundamental physics principle at play right here. Double bonds are generally much shorter than single bonds. Why? Well, because sharing 2 pairs of electrons concentrates a much greater quantity of negative charge right between the 2 positive atomic nuclei. This dense negative center acts almost like a powerful magnet, creating a greater force of attraction that physically pulls the atoms closer together. And that results in a significantly stronger bond. We quantify this exact strength using bond energy, which is the precise amount of energy needed to break 1 mole of a given bond, strictly measured when the molecules are in a gaseous state.
These are the key points related to this topic. Focus on them carefully as they are considered essential for your exams.
Let's put some hard numbers to this so you can really see what I mean. Notice the stark trend here. As we move from a carbon-carbon single bond at 350 kilojoules per mole to a double bond, the required energy jumps up to 610, and the physical length shrinks from 0.154 nanometers down to 0.134. We see the exact same massive jump with carbon and oxygen, jumping from 360 all the way to 740 kilojoules per mole. Why does this matter? Because bond strength totally dictates reactivity during molecular collisions, and it directly answers our opening mystery. Unreactive nitrogen's triple bond requires a massive 994 kilojoules per mole to break apart, literally double that of oxygen's 496. Nitrogen essentially shrugs off collisions, remaining peacefully stable in our atmosphere, while those weaker oxygen bonds break much more easily to fuel the reactions that keep us alive. Okay, let's lock all of this in with a high-yield summary of every core concept we've mastered today. We established that single covalent bonds share exactly 1 pair of electrons, and we visualized all those bond pairs and lone pairs using dot and cross diagrams. We learned that the rules can definitely be bent. Boron exists perfectly fine being electron deficient, while sulfur happily expands its octet. We scaled up to double and triple bonds to reach stability. We explored those freeloader coordinate or dative bonds. And finally, we tied it all together with the physics. Shorter bonds pack a higher negative charge, making them much stronger, and proving that reactivity depends on bond strength, polarity, and bond type, whether it's sigma or pi. As we wrap up this explainer, I want to leave you with a bit of a provocative question to chew on. If microscopic bond strength and polarity are the ultimate deciders of chemical reactivity, how do these completely invisible architectures dictate the entire physical and biological world you can touch right now? Think about the water you drink, the plastics you use every day, or even the very DNA inside your cells. It all comes back to this. Thank you so much for joining me in class today. Keep that curiosity sharp, and I will see you next time as we continue to decode the universe.
Important terminology for this topic is shown on the screen, arranged according to various exam boards. These terms demand focused attention during revision as they are highly significant and must never be overlooked. Furthermore, a past paper evaluation is included for each board and paper format. Give this paper attention too, since it will strongly enhance and refine your preparation. Additionally, aims to grasp the meaning and usage of every term instead of rote learning them individually. Consistent practice of these terms in past paper questions will greatly boost your precision and overall exam results.
Please subscribe our channel to get more educational videos. Thank you.